The Poisson point process is a mathematical model for randomly occurring events. In this video, we'll explore how to simulate and visualize the Poisson point process using R and ggplot. To introduce these concepts, let's start with an example. Imagine planting seeds in a row. Assuming there is nothing to guide us other than a straight line, we can make a few assumptions. One would be that the location of a planted seed does not depend on the location of the others. And two, the average number of seeds planted in a fixed length is a constant value. To get started, we need to decide on a strategy for planting seeds. One way to do this is by modeling the distances between them. Let's say that these distances come from an exponential distribution with rate lambda. Here lambda is the expected number of seeds per meter. We define this variable in R here, equal to 5 meters. We also define the length of our row, equal to 10 meters. Given a length for the row, we need to decide on how many samples from this distribution to take so that the row will be filled. We can use the properties of the exponential distribution and of the expectation to come up with a rule for this. So from the exponential distribution, we know that the expected value of an exponentially distributed random variable is equal to 1 over lambda. And if we have a variable that is a sum of random variables and take the expectation of that, that is equal to the sum of the individual expectations. So based on this, we can see that the expected value, dn, equals n over lambda. Now we want this to be equal to our row length, or perhaps even larger than our row length, to ensure that we take enough samples. So one way we might do this is we might set n equal to r multiplied by lambda, which would mean that the expected value of dn equals r times lambda over lambda. The lambdas will cancel out and it'll be equal to r. In this code block is where we gather these samples. On this first line, we sample the distances between the seeds from an exponential distribution with r times lambda times 2 number of samples and the rate equal to lambda as defined before. So here we've got this extra 2 just to be sure that we take enough samples to fill the row. We then create a data frame out of these sampled values. Although we don't use the raw values directly, we take the cumulative sum of these values. We have a data frame with a variable or column name planting locations that holds the values d1, d2, all the way to dn, where d1 will be equal to lowercase d1, and d2 will be equal to the sum of the first 2 values, and so on. In the third line, we simply take our data frame and filter the values of the locations for the ones that are less than or equal to our row length, as these are the ones we want to plot. In this final line, we create a new data frame out of our existing planting data frame, where the idea of this data frame is to count the number of seeds within each 1 meter interval starting from 0. So here we divide up the planting locations into bins 0, 1, 1, 2, and so on. We count the number of seeds within each bin. It's here. And then we also take the midpoint. And the midpoint is just so we can make a nicer plot. Here's the code block for plotting our samples. So we use ggplot, and the main work is done by this function here, geomjitter, and this one, geomtext. The geomjitter is much like something you would use to create a scatter graph, where you have an x and a y, then you plot points based on those coordinates. The only difference is geomjitter allows us to add some noise to the x and y, which can be useful if there are a lot of overlapping points. Geomtext is also much like this idea, plotting points based on their x and y coordinates. However, instead of plotting points, it plots text. So the plot that the code produces is now shown here. On the x-axis, we have the locations of the planted seeds, and on the y-axis, the single row that the seeds are planted in. Above each 1 meter interval, we have the number of counts within that interval. So one thing we can see from this plot is that within each 1 meter interval, number of counts is not a constant value. Here there are 2, and here there are a lot more, 7. We can even get more, equal to 9. So what this is it's a sample from a Poisson point process. The Poisson point process is a mathematical model for describing random events. In the example here, points on the positive real line. In fact, for a sequence of events that are generated according to a Poisson point process, the number of events in an interval is a Poisson distributed random variable. Let's look at some more samples from the Poisson point process. Returning back to the planting example, a field has more than just a single row, all of which need to be planted. Let's simulate the distribution of seed plantings in these other rows. So to generate this plot that shows more rows, we proceed much as before. However, instead of taking one sample, we're now taking sample n number of samples. I've set sample n equal to 5,000. So what this code is doing here is it says 5,000 times we're going to create a tibble or data frame with this column, planting locations, that takes a sample from the exponential distribution like we had before and calculates its cumulative sum. It's then going to combine all these together here to create one large data frame. Now we know the differences between samples because we've included this row index here. So by looking at the row index, we know what sample the value comes from. The only difference in the plotting function here is that we filter the data frame before doing anything else with it. So here we take the planting data frame and we filter it for rows less than or equal to n rows, where n rows is 20. This is because we don't really need to show all 5,000 samples, and 20 is sufficient. So here are 20 samples from the Poisson point process. If we look at any one row, we can notice similar characteristics to the first sample that we took. Points can bunch up or they can spread out. Now that we can view multiple samples in one go, we can also spot that there are no obvious dependencies between seed locations. We might notice that the distribution of planting locations covers many of the values on the x-axis. So we could almost say that the distribution of planting locations is uniform. In the next video, we will continue through the notebook and look at a method for empirically verifying this uniformity. I've included a link to the notebook in the video description, so please take a look and follow along.